So I guess first and foremost, exam 3, I posted a blank one. Go through, do it. Oh, I guess I should pass that on. Complete all the multiple choice, turn that in Wednesday. I will go through and then run the multiple choice through the Scantron, and then I will actually go through and report scores. I figured this way we can get more time. You guys can actually make sure that you understand what's going on with those questions and reduce perhaps some of the stress. Largely because the average wasn't very good. Probably going to be on par with what we would expect on the ACS test as far as scores, but it would be nice to kind of artificially inflate your scores now. So yeah. So yeah, go through, complete it. We'll scan it, and you'll get hopefully much better scores. Okay? Talk to whoever you want to, classmates, tutors. I don't really care. The only thing would be not really me. You can try and run questions by me, and we'll see. Maybe I'll help, maybe not. Kind of just depends on perhaps my mood. Am I shifted way over? What the heck is going on?
Do we get to see what we got previously too?
After I get everything graded, yes. Okay. So we have 6 lectures left for the rest of the semester. We're going to talk about carboxylic acids and amines. Really, I don't think there's a whole lot within the carboxylic acid chapter that's new. Ultimately, what we're looking at is right here is pretty much all of the chemistry. We're looking at our basic kind of general structure of what we could classify as a carboxylic acid. We're looking at the carbonyl bound to some kind of leaving group. In the case of the carboxylic acid, strictly carboxylic acid, it's a little bit different. Okay. Why is the carboxylic acid with our OH leaving group different than any of the other leaving groups? Yeah, but a lot of those are pretty bad leaving groups. Could argue that all of those are bad leaving groups. Yes. So the main reason that carboxylic acids are kind of get their own separate section is because that hydrogen is now acidic. Okay, so that's the primary difference between the OH as your leaving group proportion on your carboxylic acid versus any of the others. Okay? So we'll talk a little bit about some acid-base rules and some simplification things to go through. That is a favorite on the ACS test, ranking acidities of individual functional groups or individual structures. Okay? So you will see those. You need to be familiar with what rules to process. The rest of the carboxylic acid chapter is ultimately really addressing that carbon, okay, our carbonyl carbon, which really isn't all that new because we've looked at carbonyl carbon chemistry before. We saw that where we went to really, really bad leaving groups and we had carbons and hydrogens. In those cases, if it was a carbon, what functional group did we look at? Another way to draw it, could have drawn it like this, or for the other one like this. We're looking at our ketones and aldehydes. Okay? We really are not talking about anything more as far as the chemistry goes. When we look at the carbonyl, that carbonyl carbon is electrophilic. All of these cases in our carboxylic acid chapter, the carbonyl is still electrophilic. Okay? And with each of these cases, you end up doing the exact same chemistry again. So you look at the oxygen nucleophiles, the nitrogen nucleophiles, your carbon nucleophiles, and your hydrogen nucleophiles. All of those are then changing the structure accordingly, depending on what leaving groups we have, and changing your end results. Okay, but ultimately that's what we're evaluating in each of these cases. Okay, so in my opinion, I think the lecture slides are a little bit more convoluted than it's really necessary. Ultimately, what I would say you need to be able to deal with, and we'll keep coming back to this image, and I'm going to try desperately to get something like this built, is that what we are concerned about is with each of those leaving groups, how can we interconvert between them? Okay. Well, any ideas which one is going to be probably the most reactive carbonyl compound? As a hint, it's probably not any of the species in the middle. Okay, we're looking at either the chloride or the nitrogen as our leaving group being the most reactive. Why do you think the Cl is the most reactive? What's that? It's a good leaving group. The chloride ion, in each of these cases, we're looking at a negative charge coming off. The chloride ion is a great leaving group. Okay, so that's going to facilitate that carbonyl reacting because each of those other species don't have as good a leaving group. Okay? So that would then make our carbonyl with the chloride the most reactive species, and then it progressively gets lower. Okay? And why this becomes important is how do we interconvert? Okay? If I wanted to convert, say, the carbonyl with the nitrogen on it to the carbonyl with the chloride, easy or hard? It's a really hard thing to do. We're starting at a very low energy or low reactivity, and we're trying to generate something that is very high reactivity. So ultimately, to make the species at the top, there's very particular reagents. Okay? And we can really only use that one reagent to allow that to form. Once we've got that most reactive species, though, we can then work our way down to each of those other intermediate stages relatively easily. Okay? So if I wanted to convert, oops, that was probably not what I wanted to do. I wanted to convert my chloride into, say, that one. What do I need to add? What piece is missing? That piece. Because our chloride starting material is so reactive, all I've got to do is add that nucleophile, and it reacts, done, I've got my product. Okay, there isn't anything to worry about. Whereas if we looked at the reverse situation, if we tried to convert between our nitrogen to the chloride, we can't just add Cl minus. Okay, because that chloride is an extremely stable species on its own. It does not want to react to kick off that nitrogen. Okay? So what we're trying to do is effectively say at that chloride top position, that is our absolute most pinnacle reaction, reacts the fastest, most efficiently, but it takes a lot of effort for us to get it up there. It's very special reagents to get that conversion to occur. Okay? Any stage in between gets us progressive, or still gives us access to some chemistry, it's just a little bit less reactive. Okay? It's almost like the activity series, yeah. Okay? As long as we want to work our way down as far as reactivity, all we really have to do is supply that extra nucleophile. So for instance, if I want to go from the say from this guy to our nitrogen one, the only thing I really need to supply would be whatever that nitrogen piece is, and it will react nice and smoothly and go very, very well. And that's because our nitrogen-containing thing is lower in that sequence. Okay, so as long as I put in that nucleophile, it will go through and react and generate my product very, very efficiently. To go up in that sequence, not as easy. Okay? Generally, to go up, we have to switch out our chemistry to do that full jump all the way up to the chloride and then work our way back down. Okay? So that's what a lot of the overall reactions are going to be. They are very, very repetitive for that reason. Okay? As soon as we put in a nucleophile, it's going to react with that electrophilic carbon, or we decide that it's not reactive enough and we have to up the reactivity of it. Okay? Yeah.
Did you put those in order?
I put those in order, yeah. I think I did that right. I almost always get the bottom three messed up, but I think I've got that. Okay? So really that is the carboxylic acid chapter. Okay? Our primary focus, as far as your ACS, carboxylic acids are acids. They are more acidic than almost any other functional group that we've seen. In fact, they are more acidic than any other functional group we've seen this semester. Okay? After that, how do we change that overall structure to generate these new functional groups? So if we had to go through and name these, they get slightly different names. Sometimes you'll see them as acids. So this can be named as an acid chloride. The other name you'll see is an acyl chloride. Okay. As we move down, we end up with different names for each of these. This becomes, an anhydride. Next one you guys should know. What's the next one? We have an ester. We've got the acid. And the last one we have an amide. Okay. Chemistry is all very, very similar as far as each of these goes. Usually any of the reactants that we'll talk about with the acid chloride can show up with any of the other species as well. Okay. For the most part. You had a question?
Just wondering why it's in quotes.
Because what we're talking about when we look at the carboxylic acid chapter is not just carboxylic acids. In fact, most of the chemistry is around your acyl chlorides, your anhydrides, the ester, the amide. So you see a lot of other chemistry show up in there. It's not just carboxylic acids. They just all kind of fit under that pseudo-similar pattern, a carbonyl with some kind of electronegative element. Okay. Other questions? Okay. Another thing to just kind of forewarn you on, I am going to try and burn through slides as fast as I can to ultimately get us to the point where we can start reviewing material, because I think that's going to be more relevant. Okay. So the last week I'm hoping will just be review for the ACS test. Okay, going over first semester and then try and pick up key reactions in the semester. Okay, so on that note, carboxylic acids get the ic acid name. Okay, they are our highest priority functional group. So if we remember those priority boxes that I put up earlier in the semester and try to put up in each of these, they are the highest priority functional group, which means our chain needs to include that. There are some weird exceptions, like they gave you a nice one here. If we have the cyclohexane, the carboxylic acid is not part of the ring. So how could we possibly name it? And that's where you come up with this dumb name. You just name it as the carboxylic acid and then whatever the other piece is. Okay. I would doubt that you'll see that on the ACS test. More than likely what you'll see are the ic acids, okay, as far as the ending goes. There are some common acid names, like the formic acid, your acetic acid, and the benzoic acid. Those aren't as kind of straightforward as far as names go. The rest of them you should be able to derive from your standard rules, okay, your standard alkane rules. Okay. If you have two acids, just like if you had any other two of any other functional group, name it as the di. So you just include the dioic acid, because we can't get repeating i's. We make it, instead of an ic acid, an oic acid. That's not always the case. Again, they threw in some common acids. One of these we've seen before, right? Which one have we seen before? Okay, we've got the malonic acid, which we used as the malonic ester. Why did we use it as the ester and not the acid? Okay, why did we want it with those as R groups as opposed to hydrogens?
So that
wasn't leaving.
The alpha carbon would be deprotonated, not the.
We want to make sure that the chemistry was focused previously around the alpha carbon, okay? And we were relying on that hydrogen being acidic. So we had a base and wanted that position to react. If we'd used malonic ester or malonic acid instead of the malonic ester, what would the problem be?
Might deprotonate the OH.
Might.
You wouldn't.
Carboxylic acids are much more acidic than any other functional group. It would deprotonate those positions first, okay? Which makes things problematic because even if we do remove that hydrogen and add enough base to then deprotonate, we now also have nucleophilic oxygens, okay? So we want to kind of limit that ability as much as possible. So when we worked with it, we dealt with the ester primarily to limit that acid characteristic, okay? This you will see show up every so often. I don't know why this stuck in my head for some reason. But when we go through and look at some of the more complex structures, if we're just going to look at, okay, and we ignore whatever our R group is out here, we can refer to that as the O8. So when we deprotonate benzoic acid, you might have heard this before, sodium benzoate, okay? The O8 is just referring to that piece. Does not necessarily mean that it's negative. Okay? In fact, in the case of sodium benzoate, we're really implying that it's not negative. Okay? How do we know that it is negative in actuality? It's a good 150, 130, 151 question. What type of bond do we have between oxygen and sodium? It's an ionic bond, so it does separate into the charges. Okay? If we were going to make that instead into a methyl group, so instead of it being sodium, it is now CH3. Let's actually make that bond. What's in blue? It's still benzoate. What's the extra piece that's not covered? Methyl. So how do we name that? Methyl benzoate. Okay? Which is now how you would name esters. You name your carboxylic acid piece as your O8, and then whatever the rest is, you just name that as an extra substituent attached to it. Okay? So it's kind of a neat thing to remember as far as your O8s go. That actually had a little bit more information on it. We are looking at this reacting to 100%. It should be 100% because our carboxylic acid is the strongest acid here. We could go through and evaluate pKa's. Anybody know the pKa of a carboxylic acid? Did you say 5? That's pretty good. I usually say about 4, but I think you're probably fine with 5. I usually do 4.3, something like that. What's the acid in your product? A little bit of a trickier question. Is the reaction balanced? Missing H2O. What's the pKa of H2O? Would usually approximate 16. It's again one of the weird numbers that is stuck. I think it's actually 15.7. Based on our pKa's, which way should the equilibrium favor? Should favor the product. Why?
Stronger acid is dissociated.
Okay, our reactions are going to push away from our strongest acid, so lower pKa's means more acidic. So we want to go to our highest pKa. Okay? That can help you predict a lot of your acid-base reactions if you have some understanding of what the pKa's are. Okay? So, like I said, a large portion of this material is looking at ultimately just a carbonyl with some extra atom attached to it. Your textbook is going to refer to that atom as atom Z, okay, or some heteroatom. So we've got chlorine as a possibility. We've got a group of atoms, so we can look at effectively another carboxylic acid or a carboxylate attached to it. We can look at an alcohol attached to it or even an amine. Okay? So those are going to be your primary shifts through dealing with those extra functional groups, your acid halides, the anhydrides, your ester, and then the amide as well. We will also look a little bit at the nitrile. Any ideas why the nitrile might be grouped in with this section of the material? Interesting idea is referring to it as nucleophilic, but it should be grouped in this chapter because it matches the chemistry of your acid chloride. What did we say was our reactivity of our acid, or of our, sorry, not our acid chlorides, our acid compounds? It's the carbon. What about that carbon? The carbon atom is not acidic. What atoms are attached to the carbon atom? Electronegative oxygen and an electronegative halide in the acyl halide situation, which makes our carbon very positive, which makes it an electrophile, not a nucleophile. Okay, so what happens when we look at the nitrile? If we're going to group the nitrile in with the same chemistry, what would we expect our nitrile to be?
That's what I was referring to, the carbon and the nitriles.
Should be very,
That's what I was saying, it's nucleophilic or negative.
it's not nucleophilic, it is electrophilic. Okay, what we're trying to do, if we're going to put it in the same chapter, we would predict the chemistry to match. Okay, does that chemistry indeed match? Well, let's take a look at that structure. What's the most reactive thing in that compound? Pi bond. Where are those pi electrons going to spend most of their time? Why with the nitrogen?
More electronegative.
It's more electronegative. What charge does that carbon build?
Electron positive.
The carbon becomes positive, which makes it electrophilic. Still not nucleophilic. Okay? So our nitriles are also discussed, not to great detail, but there's definitely a lot of reactions with them because they are still electrophilic. That carbon is electrophilic. Does it really make sense for us to group it in there? We're looking at a carbon in the nitrile with 3 bonds to an electronegative element. Take a look at your acid system. Okay, we look at the upper right-hand corner again. We're looking at our carbon with 1, 2, 3 bonds to electronegative elements. Okay, they are effectively the same thing when you boil down their overall similarities. Okay, so the nitrile chemistry is very, very similar to your acid chemistry. That carbon is going to be very electrophilic. It will react very similarly with the same types of species. Okay. Nomenclature for your halo acids. Instead of it being with an ic acid or even the O8, though we could go with the O8, you'll see it show up with this oil chloride. The reason we would name it in that case is because we're suggesting that the chloride is our primary group. Okay? You'll see varying or variations off of this. It's just something to be aware of. I doubt that you're going to see a specific nomenclature question on your ACS test over your acid halides. Okay? Your acetic anhydrides, your anhydrides will get named as the anhydride, which is referring to the grouping of the 3 atoms in the center. Sorry, that's not 3 atoms, that's 5. And then we're naming the pieces that are extra on top of it. Okay? Usually from where it's coming from, okay? How we generated those pieces. Almost always with the anhydrides, you'll see them as symmetrical. Any idea why we see them as symmetrical? What's the most reactive piece within our anhydrides? As with all of our acids, our most reactive piece is the carbonyl carbon, which is electrophilic. Is there another electrophilic carbonyl carbon in that structure? Yeah, right next door. Why would we want this to be symmetrical? If we're going to react an anhydride, we're going to put in two electrophilic sites. If those electrophilic sites are different from each other, what's going to end up happening to your products? You're going to get more than one product. So typically when we look at our anhydrides, they're always symmetrical because we only want one product. Okay? We don't want a big mixture of different things. In this case, if it's not symmetrical, you can name each of the pieces attached to it. So again, we're naming everything based off of the anhydride, which is our piece in the middle. And then we try and name the additional things as pieces attached to it. Kind of, sort of. Just kind of the overall. The acetic is that piece. Okay, so we've got the acetic, we've got the benzoic, effectively, and then if you combine everything, we now have it as an anhydride. So we're trying to end up naming each of the individual side pieces. Again, not a huge issue, just something to be aware of when you're putting it together. Your esters, you will probably see esters show up, though I'm not positive. You're naming your substituent as it's attached to the main carboxylic functional section. So within our first case, we have the acetate, which is, again, one of those common names, there with an ethyl substituent attached to it. Okay? So we name our esters based off of the carboxylic section of it, and we lead it off with whatever that extra piece is as a substituent. Okay? Questions? I know, we're kind of pushing fast through nomenclature. Oh man, I hate nomenclature. With our amides, same general idea. You're trying to make reference to the change. So we're still looking at that kind of acetic-ish portion, and we're now changing that out. We have that acid part, except now instead of it being an acid, we have the amide. So we just change the name around. Okay? How is this different than if we had drawn out this piece, which I guess we haven't officially talked about? What functional group do we have in here? An amine. Any guesses how that's going to be named? The amine is higher priority than our carbons, so we have an ethyl amine. What's the difference? The N versus the D. The D in your amide is referring to the presence of that carbonyl. Okay, so you need to be aware of that very subtle change in your name. Okay. Oh, this one's actually kind of important. What happens if your nitrogen, so in our first case, all these cases we're looking at our nitrogen with hydrogens attached to it. What happens if they aren't hydrogens? If we now make them an alkyl group? Okay, that's going to complicate how we go through and name this. By definition, one of the things that we've decided is that when we attach something to a nitrogen, okay, and our structure is more complex, we'll make reference that we've put that substituent on our nitrogen by saying N-methyl, okay, because we can't number it, because numbering is exclusively for carbons. So in this case, we end up saying N-methyl to say that that group is attached to the N, or our nitrogen atom, within our structure. What happens if we have two R groups attached to our nitrogen? Well, just like if we had two R groups attached to any individual position, we had to number both of those positions. Okay, so if we had this guy, we've got a butane, right? We have a dimethyl, and it gets numbered as 2,2-dimethylbutane. we specify the number for each and every single one of our substituents. Same thing's going to happen when we're looking at R groups with our amides, okay, or even for that matter, our amines. So in this case, we have two methyl groups. To specify that they are attached to the nitrogen and not somewhere else in the structure, we'll have to specify an N for each of them, specifying that they are both attached to that nitrogen. What happens if you have more than one nitrogen with different R groups? It's a good question. I don't really know. I think it ends up getting called N and N prime. Okay? And then you'd have to differentiate when you put the structure together for your different nitrogens. Okay? Because I don't think that's in here. No. Good. Hi. With your nitriles, in case you couldn't guess, they get named based on nitriles, and then you name the rest of it as a kind of substituent on your nitrile. Okay? Again, not super common as far as nomenclature, or as far as your nomenclature goes, but you might end up seeing it show up. Okay? Questions about any of the nomenclature? We went through it in such depth and detail that, of course, you guys would never have any questions about it. Okay. So, properties of your acid, which I think is going to be a lot more important. Okay. First and foremost, the most important thing that you need to be evaluating within this is that we are looking at the carboxylic acid functional group acting as an acid. It is a proton donor. It will give up that hydrogen. Okay. After that, we can start to do some other nuances within it. Okay. The structure is planar geometry, and that all comes down to which atom? That carbonyl carbon having what hybridization? sp2, which is then going to force that planar geometry. Okay? We could take this a step further, because when they're saying this, I don't think they're referring to just the atoms within that plane. They're also referring to that oxygen and hydrogen. Why would our planar geometry actually shift all the way out even towards our hydrogen? Why would our hydrogen not pop out of that plane?
Least steric hindrance straight off. 90 degrees, if that makes sense.
Why did we not try and draw it this way then?
Hydrogen bonding?
It's going to have to do with hydrogen bonding. So we could try and make the argument you're talking about with least steric hindrance, and I think I would actually make the argument that if we pulled that hydrogen up and out, so it's now coming up out of the plane, that it actually has the least amount of sterics. It's now far away from everything. There's no other atoms in that plane. Whereas as soon as we bring it into the plane of the structure, it's now in the plane of both the oxygen or the R group. And if we then push that further into evaluating where does the hydrogen prefer to be, okay, we've got, I should stop drawing arrows, our blue version versus our purple version. The blue is probably the preferred arrangement. Okay, why do we prefer that blue alignment? What charges the hydrogen? Positive. To stabilize that positive, what do we need? Electron density. Our carbonyl oxygen, very close by, has that electron density to help stabilize it. You will probably force that geometry. Okay? Yes, you can vary off of that, but that's going to be your primary arrangement of the hydrogen, okay, to help stabilize that partial positive of our acidic hydrogen. Okay. The next big effect that we can see is when we start to bring two different carboxylic acid functional groups near each other. Okay. That hydrogen, being very, very positive, wants to pair up with something negative. So it will coordinate to the carbonyl oxygen of another carboxylic acid. And that other carboxylic acid will coordinate accordingly as well. What type of interaction do we have in there?
Hydrogen bonding.
Hydrogen bonding. How strong of a force, attractive force, is hydrogen bonding?
Pretty strong.
One of the strongest forces. Ionic is stronger, but at that point you're almost pushing bonds anyway. Okay, so when we look at forces, our hydrogen bonding force is probably the strongest that we're really going to have to deal with. Okay? What is that going to do as far as physical properties go? Okay, we would expect our boiling points and our melting points to be much, much higher. Okay? Because what's happening when we melt or boil? We're taking two molecules and we rip them away from each other. If they have very strong forces holding on to each other, then it's going to take even more energy to rip them apart. So when we look at the boiling points or melting points of our carboxylic acids, they are almost always much, much higher than similar structures without those functional groups. And that's what they're trying to show here. If we take a look at acetic acid, its boiling point is 118 degrees Celsius. If you look at isopropanol, relatively similar structurally, so we could kind of overlap those structures, and we still even have hydrogen bonding. Okay? Our carboxylic acid is a vastly higher boiling point. Okay? And that's because instead of having just that one of those hydrogen bonding interactions, we get two between those molecules. Okay? So we have a lot of very strong forces within your hydrogen or within your carboxylic acid functional groups. Okay? So it's definitely going to elevate those boiling points. Okay? The next issue is looking at acidity. Definitely didn't have time to draw in a structure here. Whenever you're looking at acidity, every single time, I would highly recommend that you draw it out. And what we're evaluating is looking at the stability of the conjugate base. Okay? Everybody has their own little methods that makes it easier for them to deal with. When it comes to acidity, I always look at the conjugate base. Okay? That, to me, is the most helpful thing to evaluate. And what we're trying to do is say if that species is stable, if our conjugate base is stable, that means that H plus can come off. Well, if H plus comes off, we're saying that our species was very, very acidic. So the initial one was very acidic. Okay? So to decide and rank that stability, there are a variety of methods that you should be going through and doing. The first thing to evaluate would be charge. Okay? If the species is not charged after it lost the hydrogen, okay, well, charge is the most reactive thing. So if it's not charged, that species should be very, very acidic. Okay? For an example, if we look at the acidity of H3O+, what happens when it gets rid of its hydrogen? We end up with H2O and our H+. We evaluate our conjugate base. What's its charge? Neutral. Okay, which means that species is incredibly stable, which means what about the H3O+?
Very acidic.
Very, very acidic. Okay? So that's your first pass through. The next part is looking at where that charge is located. Okay? There's two things to evaluate when you're doing that. You're looking at size and electronegativity. Size will trump electronegativity. Okay? So let's take a look at another couple examples. If we wanted to look at the acidity of NH3 versus H2O. All right, well, the first pass, get rid of the hydrogen. And now we want to evaluate. Again, we always start with the beginning. Is there a charge? Yes, it's the same in both cases, so we now move on to the next set. Where is the charge? Okay, the charge in our NH2 is on our nitrogen, whereas in the OH, it's on the oxygen. So now we want to evaluate the stability of that charge. So first, size. Is there a size difference between the oxygen atom and the nitrogen atom? So you'll hear yeses and nos depending on how you were trained to look at this. When you compare size across a row, changes very, very small amounts. Okay, so yes, there is a change within size, but within an individual row, at least as far as organic chemistry is concerned, there is no change in size. Okay, they are all the same. Okay, which means in our first pass, where the charge is, nitrogen versus oxygen, there still isn't a difference. So we would now evaluate electronegativity. Which one is more electronegative? Oxygen. What does electronegativity measure? How well it holds which electrons? Bonding electrons. Okay. Oxygen wants to hold those electrons more than nitrogen does, which means OH is more stable, which means H2O was more acidic. Okay. Do we need to see a size example, or are you guys happy with that? Okay. Next thing to worry about is resonance, which I would equate to size as far as a comparison. Okay. How can we equate that to size? What happens when we look at the carboxylic acid? We look at its conjugate base. We've got that oxygen with the negative charge, which with the example so far, that's actually pretty reasonable. But what can we do with that negative charge? We can spread it across the atom and put the negative charge on a different oxygen atom. Effectively, what we have done is put that negative charge and spread it over a larger area or a bigger size. Okay? So resonance will do a lot to stabilize that charge and then make that conjugate base more stable, which then makes your acid even more acidic. Okay? Last one that I would really push would be looking at inductive effects, which the textbook for some reason did a whole bunch of examples on. If we see no other difference, but we notice that there are withdrawing groups or electronegative atoms nearby, those are going to start to draw electron density through these sigma structures, so no resonance, through the sigma bonds, pull electron density further and further away from that hydrogen on the end. Or what we can do is look at it as the negative charge being drawn into the structure. Okay, so that would be your inductive effect. If you still do not see a difference at that point, guess. Okay, you should absolutely have seen a difference at that point when it comes to the ACS test. There are other things that you could evaluate as far as stability. You can look at solvent effects and other things along those lines. I doubt you will see that on the ACS test. Highly, highly, highly doubt. Okay. So we can look at pKa's, which we've already done. Our pKa values for our carboxylic acids are up in that 4 range. So if we look at our standard equilibrium, we generally see it favoring, what are they trying to show here? Oh, in water, that's why. If we go through and evaluate that top situation, our carboxylic acid is the more acidic. How do we know it's more acidic than water? pKa value, which means our carboxylic acid, having the smaller pKa, is more acidic. It will be the acid on our left-hand side. So we can shift to the product side. Where's our acid on the product side? H3O plus, which has a pKa of... Nobody knows it, then I can guess and be okay. I think it's about negative 1.5. Okay, yes, you can have negative pKa's. What does that mean? It's really, really acidic. Okay, so we take a look at our pKa values across this, and what do we end up deciding? That if we just throw a carboxylic acid into water, what happens?
Not much.
Not much. It stays the carboxylic acid. So when does this chemistry become more important? Well, when we throw in something else. Water on its own isn't going to do anything with a carboxylic acid, okay? Which is why when we mix acetic acid and water, what happens? Not a lot, okay? Look at your vinegar solutions. Your vinegar solutions that you would add to your salad dressing is a mixture of water and acetic acid, okay? So we don't see a whole lot there. The pH will change a little bit on us, but it's not going to be that big of an issue. Where it becomes more important is when we add in something else that's basic. Okay? Next thing to go through and do is evaluate what happens if we change the structure of our carboxylic acid. You'll note in each of these cases that we do see some substantial shifts. Okay? Why do we see these shifts? Why is that first one more acidic than everything else? It is an inductive effect. We don't actually get any resonance. okay, which is kind of odd in that case. What we're looking at is an inductive effect effectively coming from that carbon. Why is that carbon being an inductive effect? What's the difference? sp3 versus sp2. The sp2 is more electronegative than your sp3. That is inductively drawing electron density away. You might be suspicious that we do get a resonance effect. For there to be a resonance effect, we would have to pull electrons from our oxygen all the way into the ring. You'll find that you cannot do that. Okay? It doesn't make physical sense. If anything, you would see the ring donate electron density out, which would then do what to the acidity?
Decrease.
It would decrease it. Okay? That's going to put more electron density out there, stabilizing that OH bond. Okay? So what we're seeing in that case is an inductive effect. What about between the next two? Where's our difference now? And one thing we can do to help what we're ultimately comparing is carbon and hydrogen. What's the difference between carbon and hydrogen? Carbon has more electrons. If we have more electrons, what does that do to that OH bond? It's going to end up strengthening it, okay? Because we can put more electron density into that. The more electron density in the bond, what happens? The stronger the bond it is. Okay? You'll notice that that isn't a huge change, okay, but it is big enough that we could address and come up with a theory to explain that. And that's ultimately what we'd be looking at, our hydrogen versus our carbon. Okay? So always try and find where that difference is. And it may be something that's obvious. It may be something that's a little bit hidden and take a little while to kind of process through. Okay? Next one, we see big inductive effects when we look at electronegative elements. Okay? So you will see this effect happen a lot when you're adding electron withdrawing groups. Popular on ACS test questions. In fact, I think there's one just like this in the test book, right? Okay, Danica, I think I helped you and Zeno with it. Did I help you guys with one with acid? Oh. In any case, we're looking at those chlorides withdrawing electron density. If they draw electron density away from the atom that's attached to them, so what happens? That chlorine takes electron density. What happens to this carbon? Our purple carbon becomes partially positive. Does carbon want to be positive? No. So what does it do? It takes electron density from wherever it can, which happens to be from the next carbon. Now that carbon becomes what charge? Partially positive. Does it want to be partially positive? No, so what does it do? It takes electron density from the oxygen. Now the oxygen says, this is ridiculous. I'm starting to become partially positive. So what does it do? Completely removes the electrons from the hydrogen, so the oxygen can be like, I'm not positive. But the hydrogen now is. So what we're doing is slowly pulling electron density away. Okay? What happens if we add more chlorines? Well, there's now more electronegative elements to pour more of that electron density away, so we see the acidity increase, or our pKa decrease. You'll notice in this case it goes rather drastically. Okay? What happens in the second set? Okay, underneath.
Chlorine's further away, so it has less of an electron withdrawing effect.
With these inductive rules, we're just pulling electron density within a sigma bond. We can't really do much more than just a slight shift in the polarization of the bond. With resonance effects, we can draw that resonance all the way through and show that it really contributes. When we're looking at an inductive effect, all we're effectively doing is moving the electron density just a little bit within that bond. Well, the further away that shift gets from where we're looking at our reactivity, what ends up happening? Every step gets progressively weaker as far as the electron withdrawing effects. So the closer our electronegative element is, the more it's going to contribute to weakening that bond and making it more acidic. Okay? Questions about your inductive effects? You can go in and throw in all sorts of electron withdrawing substituents. You will need to be kind of aware of what these things end up doing. In general, as long as you can consider resonance, you'll probably be fine as far as seeing what's happening. You'll notice that when we're looking at benzene rings, when they test you on it, you will probably not see them test a Z group, whoops, in all three positions. Okay. You might actually see it at the ortho and para positions. Why? Which one would be more acidic? Orange Z or red Z? Orange Z. That sounded kind of funny. Okay, because that electron withdrawing group is closer to our carboxylic acid. Okay, why would we expect to not see a comparison with that blue Z? Whereas it was valid to look at the orange Z. Nope. Kind of. Has to do with a resonance effect. When we're looking at orange versus red, there is no resonance difference. You're looking at the ortho and para positions, which means you get identical resonance contributions, which means we'd have to look towards induction. If we look at the blue Z, it's now at the meta position to our carboxylic acid. That is drastically going to change your resonance contributions. So that resonance effect is now going to then stack on top of your inductive effect. How much does it stack? Good question. Who knows? Okay. Probably depending on what that withdrawing group is, you may see a larger contribution than not. Okay. Which is why you won't see that question. Okay. Because we don't want to test on two different things, both resonance and inductive. Okay. Because they're both effectively doing the same thing. It's just a question of how they go about doing it. Okay, so just be kind of aware of the limitations of some of their questions. This becomes really important for biochemistry on what they're talking about here. If we take a look at pyruvic acid and we look at physiological pH, we end up not seeing the acid form. We see the carboxylate form. Why? Just a few slides ago, we said that wasn't the case. We saw the acid form. Why does it all of a sudden change? The conditions that we looked at before were just in the presence of water. Water is actually naturally slightly acidic. When we look at physiological pH, pH within the body is actually slightly basic. We're changing the starting conditions. So if you change the starting conditions, you are going to see a shift into which form is actually preferred. So when we're looking at physiological pH, anything in the human body or anything living for that, well, most things living, you're looking at the carboxylate being formed. Okay? So when you draw an amino acid, most people, when referring to the amino acid, show the amino acid not protonated. Okay? That acid is typically not protonated because at those pHs that we'd be looking at in the human body or other things, it's going to be deprotonated. Okay? So just be aware that we can cause slight shifts within the equilibrium depending on those starting conditions. Okay? It's an important observation. Overall preparations of carboxylic acids. These were all things that you guys have seen before. You've got the permanganate with heat. So your permanganate's a good oxidizer. So you can end up cleaving an alkene and turning it into two acids. You can look at the oxidation of primary alcohols with a strong oxidizing agent like chromic acid. Okay. We've also seen when we're looking at an alkyl benzene structure, as long as we have a reducible hydrogen to start off the reaction. As long as we have that hydrogen, we can go through and completely oxidize that down to the carboxylic acid, or officially to the benzoic acid. Okay? That is one that I've seen show up both in tests and on the ACS test. Remember, for this reaction to work, you absolutely must have that reducible hydrogen. If you don't have that hydrogen, it does not work. Okay? For instance, what happens? Absolutely nothing in this case. Okay, we do not get that oxidation. Sorry, I keep calling it reducible hydrogen, oxidizable hydrogen. Okay? So you have to be aware of that functionality kind of getting. Okay? It's kind of odd that the textbook decided to include these, or this section of slides here, because we're starting with what functional group? We've got a nitrile. They talk about nitrile chemistry a lot towards the end of the chapter, so it just seems a bit odd that we introduce it here. So we can hydrolyze a nitrile in the presence of an acid to generate the carboxylic acid functional group. How does it work? When we look at the nitrile, what's our reactivity?
Partially positive carbon, partially negative nitrogen.
We have the partially positive carbon and our partially negative nitrogen. Deciding between those on which one reacts first could be a bit difficult to do unless we looked at our our other reagent. What's the other reagent? Acid, okay, H plus from our water. What's going to be our first step? Nitrogen can get protonated. We then end up with now a very active structure. Why has the structure become more active? Nitrogen is now positive. Does nitrogen want to be positive? Nope. So what does it start to do? Pull pi electrons away, but now what happens to the carbon? It becomes positive, so what could we introduce to help it stabilize? Be careful with that. Why water and not OH? Okay. OH is a base. What conditions did we start with? Acid. Be very careful with your starting conditions and make sure you appropriately adjust for those conditions. Okay. This will be an issue that shows up on the sapling homework, which I will try and get up tonight. Okay. You have to be aware that your nitrogens can act as bases, and if you're running under acidic conditions, you should not be making a base. If you're running under basic conditions, you shouldn't be making something that's acidic. Okay, so you'll have to adjust for those conditions. Okay? At that point, what happens? Is that stable? Nope. What happens? Can lose a hydrogen through a deprotonation step. We then have a neutral species, which isn't so bad. Okay. How are we going to end up pushing all the way to the carboxylic acid? We're going to need a lot of water. Okay. Why do we need a large excess of that H3O plus in water? What's the other product in this reaction? What's the other piece that gets spit out? What's the issue with spitting out NH3? What is the nitrogen in NH3? It's basic and, more importantly, nucleophilic. What's its nucleophilicity in comparison to water? It's more nucleophilic. So if we really want to push the carboxylic acid, starting with the nitrile, experimentally we have to put in a vast excess of our water and acid to help push our equilibrium to the point where we can eliminate that NH3 from the structure. Okay. If we wrote out NH3 as a final answer on this, do you think it'd be correct? No, why not? What's our primary characteristic for our NH3? What's our primary characteristic for the carboxylic acid functional group? It's an acid, it's acidic. Which means if we actually wanted the carboxylic acid, we have to add enough acid into our solution that we don't have NH3, we have NH4+. Okay, so that we don't have that nucleophile. Yes?
How does heat play into that? With like the closing condensation, you get, the heat would kind of make turn the COOH into carbon dioxide.
Careful. You're not talking about the Claisen condensation, you're talking about the malonic ester decarboxylation. To get the COOH to turn into the carboxylic acid, you needed the other carbonyl. You needed an enolizable hydrogen to allow that to occur. If we add heat to a carboxylic acid, nothing happens. We're not going to get CO2 to form. Okay, so it's a slightly different chemistry. As far as why we need heat here, what did we say was the issue with nitrogen? It's nucleophilic, okay? Which means if we're looking at a reaction where now I'm trying to put in an oxygen to break a carbon-nitrogen bond, that carbon-nitrogen bond is actually relatively strong in comparison to the carbon-oxygen bond. Okay? How can I help break that bond? That can help push our equilibrium, but energetically, how can I break it? We can add the heat to help weaken a lot of those bonds and help us get to the point where we can get that NH3 out of the way and turn it into ammonium. Once it's in that NH4 state, it's not a nucleophile anymore, we don't have to worry about it. But any of these intermediate stages where I have a nitrogen with a lone pair, that's nucleophilic, that's problematic. Okay. So you'll continue to deprotonate, yep, all the way through. Yep, exactly right. Okay. I don't really feel like drawing that mechanism because it's now doing that same sequence again, and then again, and really again. Okay. Other questions on that one? I know it's only a partial mechanism. Whether you guys like it or not, I'm probably also going to start doing less mechanisms because the ACS test is now officially on us and there are no direct mechanisms. Okay? And as far as the mechanisms for this section goes, it's all ultimately the same thing. You have an electrophilic carbon, attack it with a nucleophile. Okay? So nothing really big. Oh, that's why that one's there. How do we get the cyanide on there? Get our nitrile on there. Okay, to get the nitrile attached, we're going to have to do a substitution reaction, and that's what they're trying to show at the very beginning there. So we're running an SN reaction, okay, with an alkyl halide, so we can have our cyanide group come in and do that substitution. Which type of mechanism do you think you'd get? SN1, SN2? Y2? I agree. Primary and? What about the nucleophile? It's a strong nucleophile, so yeah, I'd probably see SN2 or push SN2 in this case as well. Is it as simple as just a primary alkyl halide though? It's a resonance stabilized primary alkyl halide. Benzyl bromide would react in an SN1 reaction as well. Okay. So pushing the SN2, it's probably more the cyanide than anything else, having that strong nucleophile. Okay. So just be aware resonance can contribute. Okay? So to get your nitrile, you can just do that cyanide reaction. The other thing we can do to make our Grignards, we could react CO2, or sorry, the other thing we can do to make our carboxylic acid is that we can react CO2 with a Grignard reagent, everybody's favorite reagent. Grignards are that strong nucleophile. The carbon in CO2 is still a good electrophile. Why is it a good electrophile? We could look at a resonance effect. It's a good one. All right, that actually pushes it to the extreme.
Well, that makes a different factor.
Yep.
Oxygen is pulling electrons down.
So we have a full-on resonance effect showing that positive charge, but we can push it even further to an inductive effect. Two electronegative atoms pulling electron density away from that central core. We're looking at that carbon being a pretty good electrophile. Okay. How good of an electrophile is that? It's an interesting question. What do you guys think? What's one of the big problems in the world right now?
Global warming.
Global warming. What's one of our issues for global warming? Presence of carbon dioxide. If carbon dioxide was that good of an electrophile, do you think we'd really have that big of an issue with CO2? No. So we can get it to react as an electrophile by reacting it with something a whole heck of a lot stronger. Okay? We're looking at Grignard reagents, and our Grignard reagents have a negative carbon. So that is a wicked good nucleophile. Okay? So CO2, while it does have that electrophilic ability, isn't the greatest electrophile. Okay? So we can do that reaction. We will have to follow that up with a secondary step, adding the H3O plus as a step 2. Okay, why? Our Grignard reagent comes in as a nucleophile, right? Which means what? What charge does our R group have? Negative. So it acts as a nucleophile and a base. Which means even if we happen to have some acid floating around to protonate our carboxylic acid, it would react with the Grignard reagent first, neutralize the Grignard, and we don't form our carboxylic acid. Okay, so we have to add that H3O plus as a secondary step. Okay. More reactions of, we can look at hydrogen as nucleophiles, or hydride rather. So you have to use lithium aluminum hydride. The sodium borohydride won't do a good job with this. And that's just because we end up with reactivity issues with the acidic hydrogen. To get this reaction to work, to reduce your carboxylic acid, you will need to use 2 equivalents, actually 3 equivalents of the lithium aluminum hydride. Why would we need so many equivalents? Lithium aluminum hydride supplies what species? Hydride, H minus. Is that a stable thing? No. What is H minus going to react with? Anything that's positive. What's the most positive thing in our carboxylic acid? What's the most positive thing in our carboxylic acid? We have the hydrogen, or acidic hydrogen, on the carboxylic acid. Our lithium aluminum hydride will react with that first. So the very first step of our reaction is actually an acid-base step. Okay? So we would deprotonate our hydrogen, or our carboxylic acid first. We could then follow that up with our reducing equivalents. And now our carbonyl carbon is the most positive thing present. Now our hydride can go through and react. Okay? That would then stall out at our aldehyde. What's the issue with our aldehyde, particularly in the presence of lithium aluminum hydride? Do we still have an electrophilic carbon? Yep. The carbon in your aldehyde is also electrophilic. Lithium aluminum hydride is an extremely strong reducing agent. Remember, it's the strongest one. It will completely reduce that down to the alcohol. once we form the aldehyde, it will react before our carboxylate. Okay, so once we reduce so we run through our reaction, we can convert everything over to our carboxylate. Then our first equivalent of our carboxylate can react to form our first aldehyde. Which is going to react first, the aldehyde or carboxylate? As a slight hint. What does our carboxylate have? It has resonance, which does what to the stability of the positive charge? Our electrophilic carbon. Makes it more stable. If it becomes more stable, what happens? Less reactive. As soon as we form one aldehyde, the aldehyde reacts in preference. Okay? Once we've gotten rid of the aldehyde, then our carboxylate can react again to make another equivalent of the aldehyde. Whoop, now the aldehyde reacts again. Okay? So we would need multiple equivalents of the lithium aluminum hydride to react across our carboxylic acid because of all of those potential reactions that will occur along the way. Okay? We can't use sodium borohydride, but we can use a slight variation of this. We can use BH3, and this will also work with your reductions. It's a little bit more selective. It won't react with ketones, but it will still react with the aldehydes and kind of reduce down, which is nice because then we can keep our ketone but lose the carboxylic acid. Okay? Cool. I think I'm okay with stopping at that point. Really, for the rest of this, it's now going to be going back over all of those derivatives. So what we're going to end up effectively relating now is what happens when, instead of being a carboxylic acid, we now change that OH into a different heteroatom. Okay? And we're looking then at converting in between all of these possibilities. Okay? Questions about that? I know that was exciting. I was kidding. Okay. So we'll go ahead and leave it there, and we'll pick up on Wednesday dealing with all of our derivatives, because that was effectively an hour. Okay? Since you guys seem awfully excited, we'll just go ahead and leave it at that.